Okay, so again, make sure if you've not finished up 3.1 that it is due tonight. Okay, that worksheet we just finished up. Now we're going to talk about differentiability. You have a Math Excel assignment. I think it's only 10 questions. Due Wednesday by midnight. When we come in Wednesday, you'll have some work time to work on 3.2. Ask me questions. We might have some sort of an enrichment activity to recap 3.2. And then we'll get into 3.3, which is where you guys want to be. Okay, differentiability. So this is actually 3.2. All right, so things we know already. We did a lot of stuff with limits. So in order for a limit to exist, the limit from the left must equal the limit from the right. Okay, you don't necessarily have to write these down. We're just kind of recapping what we've been working on. To evaluate limits, we had this big limit formula that we worked with. We could come up with a function for our derivative. We also talked about differentiability, and we're going to talk a lot more about it today. If a function is differentiable, then the function must be continuous. All right, I want to say that again. If a function is differentiable, and it'll be in the setup to the problem, it'll say this is a differentiable function, or we know that we can differentiate everywhere, the function must be continuous. Okay, which means if f has a derivative at some x equaling a, then we can say it is continuous at x equals a. Okay, if it is differentiable, we can say it's continuous. Simply saying it is a continuous function does not imply that it is differentiable. We're going to go through some examples that show that. Okay, but if we know it is differentiable everywhere, we can say it is continuous then everywhere on that interval. Okay, so when are derivatives non-existent? So again, the derivative represents the slope of the tangent line. If we cannot determine a slope between 2 points, okay, derivative is instantaneous rate of change at a point. Well, getting back to the original definition, we had that P and Q and the two slide together so we can make a line between the two. If we cannot determine a slope between 2 points, there cannot be a derivative there. But this does not mean that the function is discontinuous. Again, we're going to get into some examples to show this. Okay, so derivatives can be non-existent, meaning we cannot find a derivative, but that does not mean that the function is discontinuous either. If we can find a derivative everywhere, then we can automatically say it is continuous. But just because we cannot find a derivative does not mean that it's not continuous still. Okay. We have what's called one-sided derivatives, just like we had one-sided limits, left and right-hand limits. The reason we did all that limit work is because it ties into derivative stuff. It is the foundation of derivatives. So one-sided derivatives, if a function f of x is differentiable on a closed interval, we'll just say from some a to b, we can determine right-hand derivatives, and this is the slope of the tangent line from the right and the left. So we determine limits from the left and the right. Now we can determine one-sided derivatives, okay, going from the left and the right. Because if we're approaching some point we can see, okay, is it going to be the same derivative from the left as it is from the right? If that's the case, we can find that derivative. If it's not the case, we cannot find the derivative. Okay, there are 4 cases where f prime of x fails to exist, where we cannot find a derivative. First one's going to be at a corner. So a corner would appear in a function like absolute value of x, where it makes that V shape. If I want to find the derivative right here at x equaling 0, it would fail to exist because my one-sided derivatives differ. Slopes of the lines approaching the corner differ. Okay, I have a negative slope as I'm approaching x equaling 0, and then I have a positive slope. Okay, so like limits, they have to be the same. Okay, these ones are not the same. I have a negative slope and a positive slope, so my derivative fails to exist at 0. I could find it if I looked here at, say, x equals 2. Yeah, I can find it there. Or if I did it over here at 4, I could find it there, but I cannot find it at 0. Okay, but this is still a continuous function. Okay, I can graph this without taking my pen off my paper. This is a continuous function, but it is not differentiable everywhere. It fails at 0 because it's a corner. Okay, so the first one where it fails to exist is at a corner. Okay, second one is called a cusp. If I had a graph, for example, was x raised to the 2/3 power, creates this cusp shape right there at x equaling 0. So on this one, the slope of the secant lines, or the slope of the tangent line even, will approach negative infinity from one side and positive infinity from the other. Okay, this curve here is pronounced. I mean, it's going more and more vertical as I get closer to 0 on the x-axis. Okay, so if we have a corner, we have a cusp. Those are 2 cases where it does fail. And again, it only fails at that point at x equaling 0. I could find it at x equals 2, x equals -2. I could find those values for a derivative. And this is a continuous function, but it fails to be differentiable right there at 0. And this cusp will occur anytime we have any sort of a rational exponent. It will create this shape. Okay, third one is if we have a vertical tangent. So let's say we had cube roots of x. So if I want to find my tangent here at 0, it would create a vertical tangent. And a vertical line has an undefined slope, so it fails there. Okay, so for a vertical tangent, slopes of the secant lines approach either negative infinity or positive infinity from both sides. Okay, creates that vertical tangent, creates a vertical line. Can't find the slope of a vertical line, it's undefined. So we have corner, we have cusp, we have vertical tangent. We'll do our next one. And then the last one is if you have a discontinuity. Okay, if there's any discontinuity in your graph, you no longer have a continuous function anyway. Okay, you can't find the derivative at a point that's undefined. Okay, so for example, if I graphed simple piecewise function that says, well, it's -1 for values of x less than 0, and then it's +1 for values of x greater than 0. This is an open circle here, but if there is a discontinuity, it is not differentiable at the discontinuity. Okay? Because here the discontinuity will cause one or both of the one-side derivatives to be non-existent. Okay, we could not find it at 0. It's not differentiable. We can only differentiate if it is a continuous function on a continuous point on our line. Okay, so these are the 4 cases that we're going to work with: a corner, a cusp, a vertical tangent, or if there's any discontinuity, our derivative fails to exist at that point. Does not mean we could restrict the interval to only the continuous portion and find our derivative there, but specifically at these points, it fails to exist. Okay, so in general, and you'll hear me say this now several times, for a function to be differentiable everywhere, the graph must have a smooth transition at all points. So if we were just to look at the graph y equals x squared, okay, again, our derivatives have to be the same as we're approaching that, okay? As we're approaching it, they actually do end up being the same as we get closer and closer to that point. Yeah, it starts out being negative and positive, left and right of the y-axis, but they're eventually going to get to be 0 from both sides. Okay, so this idea of having a smooth transition is important. Okay, corner fails to have a smooth transition. A cusp fails to have a smooth transition. The vertical tangent was a smooth transition, but it created that vertical tangent, which fails. Okay, and the discontinuity had no transition. There was a jump in the one we showed. Okay, so must have some sort of a smooth transition at all points, and I'll say all points in your interval, because you can restrict the interval. It has to be a smooth transition at all points for you to be able to differentiate. And again, it has to be continuous. Okay, so let's talk about graphing again. So this just kind of goes back to what we talked about in 3.1. But the graph of f prime, we use the values in the x of f of x and f prime of x as the new y values. Okay, so that's what when we go to graph, if we were looking at that x squared graph again, and if I chose a point, say over here, and I create my tangent line, this one might have a slope of -5, but then I choose a point here that has a slope of -1. So when I'm actually graphing, if I think of it as coordinates, as x and y coordinates, my derivative graph is going to be x, comma, and then f prime of x would be my coordinates. Okay, so if I was here at, if I was over here, it has a slope of -5, and be down like this. This has a slope of -1, going to be down like this. At 0, a slope of 0, and then it would continue on. So this is represented in coordinate form, how these actual coordinate values work out. Okay, so your derivative graph is still your x value, but now your y is f prime of x. Okay, same thing right there. Coordinates of the graph of f prime will be x comma f prime of x. Okay, all right, let's do a couple examples. In this one, I want to show, meaning prove, that f of x has left and right hand dy dx. Remember, dy dx, this means derivative, which means slope of the tangent. So it has left and right hand derivatives at x equaling 0, but no actual derivative there. Okay, so negative x for values of x less than 0, and then x for values of x greater than 0. So this would go down and look like this, and then it'd be an open circle there. That's the first piece. But then it's saying it's just x for values, oh, I already graphed it, for values greater than 0. So it creates this shape, which we know is a corner. And so it's not going to be differentiable there because it's creating this corner, but it is a continuous function. Okay, there's no holes in my graph. But just saying it's a corner, it fails is not enough. I want to show or prove that it does fail to exist there. Okay, well, in order to do this, we have to do our limit stuff. So for my left-hand limit, we'll say my limit as x approaches 0, and we'll say from the negative side. Okay, and again, we're doing our limit as h, let's change this up to h approaches 0. H approaches 0 of f of a plus h minus f of a all over h. We're using this formula. So we're going to have our negative x. Well, x is really a plus h, so it's a negative of a plus h minus f of a. The actual value there is 0. And instead of a, let's actually put in our 0, because we're going to evaluate this at 0. So 0 plus h minus 0 all over h. So the zeros we really don't have to worry about. Only thing we're left with on the top is going to be the limit as h approaches 0 from the negative side. I have a negative h all over h. So I could rewrite this. I could say, well, h over h, this really just goes to 1. So really all I'm trying to find is the limit as h approaches 0 from the negative side of negative 1, which ends up being negative 1. So my slope is negative 1. All right, and we could see this, but here's the proof showing that it is negative 1. Okay, we already know that this is going to have a slope of negative 1 just from negative x. Okay, but that's not what I want to see. I want you to actually show me that the actual slope is negative 1. All right, and then on the right hand, we'll say our limit as h approaches 0 from the positive side. So now I have a positive 0 plus h, because that's my function, is just x, minus 0 all over h. So my limit as h approaches 0 from the positive side is h over h. And so that ends up being 1. My slope is 1. Okay, and then my proof, I could say, well, since the derivatives, so since the derivatives are not equal, so I'll say since f prime of x is not equal from both sides, so it's not equal at both sides, x cannot be 0 or does not exist there. So dy dx does not exist at x equaling 0. So that'd be the final piece to prove we've shown that the right and left-hand derivatives are different, therefore it fails to exist. Emily. Yep. Because we're using this function, so we're just using negative x as our function. And so if we did f of a plus h, so our function is negative x, so it's negative of a plus h. So we're not using a because a is 0, so it'd be negative of 0. So we're using this function for the left one, we're using the bottom for the right. Okay, because our interval is x is less than or equal to 0, so that's left side. X is greater than or equal to 0, that's the right side. So we have to use the different pieces based on where we're at. Okay, but this would be the proof. So this is a type of test question that I can ask you. If I say show or prove that there's no derivative at x equaling 0, you can't just say, nope, doesn't work because it's a corner. If I say show or prove, you have to show me derivatives, show me that they're not equal, make your conclusion. Since the derivatives are not equal from each side, fails to exist. Okay, but again, this is still a continuous function. All right, let's try another one. Show or prove that our function f of x has no derivative at x equaling 0. And this one, just for practice, let's use the other one. Let's say x approaches a of f of x. F of x minus f of a as x minus a in the bottom. Let's try this one. So we're going to have our limit as x approaches 0 from the left. It's going to be our function x cubed minus 0 cubed. Okay, we'll actually put in 0, so it's x cubed minus 0 all over x minus 0. So we can say our limit as x approaches 0 from the negative side of just x cubed over x, which we can simplify to just be x squared. When we evaluate that limit, we get 0. So my derivative from the left-hand side, which is the same as my slope, equals 0. Now from the right, x approaches 0 from the positive side. We're going to have 4x now minus 4 times 0. So we're going to evaluate it at 0. So that's just 0 all over x minus 0. So we can simplify that to just be 4x over x. Okay, I can't evaluate my limit directly, but I could rewrite this and say, well, x over x is really 1. So really all I'm trying to find my limit as x approaches 0 from the positive side of 4, which is just 4. So now my derivative, which is my slope, is equal to 4, which makes sense because this has a positive slope coming off of it. As I approach here, this has a positive slope, and more specifically, that slope is a positive 4. All right, so then we can conclude, therefore is the 3 dots in a triangle. Therefore, my left and right derivatives are not equal. not equal. So dy dx does not exist at x equaling 0. Simply from the graph, though, we could see this. There's that abrupt change. It's not a cusp. It's not a corner. It's just an abrupt change. It's not a smooth transition. All right. If the piece to the right of the y-axis came down as more of a parabola, then we could probably make it work. Okay. So if we just had just a basic x cubed graph, that one would work. So it'd be a nice smooth transition. Okay. My derivative was positive, goes to 0, and then it stays positive. Okay, but it does approach 0 from either side. So that one would work. This one had that abrupt change right there at 0. So it did not work. All right, intermediate value theorem for derivatives. So we've talked about intermediate value theorem, but now for derivatives. So if A and B are any 2 points, so we have some points A and B on our x-axis, in an interval in which f is differentiable. So right there, they say f is differentiable, therefore we know it has to be continuous on that interval. They tell me it's differentiable on that entire interval, it has to be continuous. Okay, so I could have something, maybe just look simple as that. Then f prime will take on every value between f of a prime and f of b prime. All right, so say we have, if we want to find the slope here at a, and we found that to be, so f prime at a, maybe we found that to have a slope of about 1. And then I picked another point up here at b. This one, f prime of b, maybe this has a slope of like 7. Okay, it's much steeper, but it's still a positive slope. So if I picked any point in here, say C, and then I found my slope here at C, the slope here at C, f prime at C will be between f prime of A and f prime of B. It's going to be somewhere between 1 to 6. Okay, if I looked at that, it might be closer to like 4, we would say, as an approximation. It's not going to be 8, and it's not going to be 0, okay? But it's going to take on some value in between those two numbers. Okay, again, that's intermediate value theorem. We did it with continuous functions. Okay, if I know I have 2 points, I can find a value in between there. Now, if I have 2 derivatives, I can find a value in between there. So the intermediate value theorem will hold. Okay, so big idea I want you to take away from this. Does continuity imply differentiability, or does differentiability imply continuity? The bottom one, okay? As simple as it sounds, do not forget this, okay? If they tell me it's differentiable, I know automatically it's continuous everywhere, okay? But simply having a continuous graph does not imply differentiability everywhere. We went through those cases: corner, cusp, vertical tangent, discontinuity. Those are all continuous except the discontinuity one, but that does not imply that we can differentiate everywhere. Okay, so differentiability implies continuity. So 3.2 in Math Excel, like I said, I think it's like 10 questions. Okay, due Wednesday by midnight. And if we think of kind of the difficulty of this course graphically, like I said, we're kind of going to go in this pattern. I would say we're right about here. We're over kind of that hump of finding the derivative using limits. Okay, this idea of differentiability is pretty straightforward. Wednesday is going to be your favorite day of the year so far in this class, in all seriousness, because I'm going to make things a lot easier for you on Wednesday. And then because I made it easier, it allows us to do a whole bunch more stuff, which takes our curve in a more positive trajectory. And so it's not a bad thing, but for a little while, you won't be as upset with me.